Thank you for coming to the CITA seminar on Friday 13th. Today we are pleased to have Thales Gutcke visit us and give us a talk. Thales is currently a NASA Hubble Fellow at Princeton University, and later she'll be also continuing as a LYRA Spitzer Junior Fellow. And she was also a postdoc fellow at the MPA for 3 years, working with the Fokker Springell. And she got her PhD from MPIA in Heidelberg, working with Andrea Macho. And she's an expert on galaxy formation simulation and also studying CGM, as well as variations of IMFs in Milky Way-like galaxies. And today she'll talk about LYRA, which is a galaxy formation model resolving the critical scales for the supernovae explosion. So yeah, Thales, is all yours. Please take away.
Thank you so much. And thank you all for being here. I don't know what all your expertises are, so I decided to give a fairly broad introduction. I hope you won't get bored. So I'm talking about LYRA, which is a galaxy formation model that I have been working on developing in the last like 3.5 years at this point. So my title, Dwarf Galaxies on Small Scales in a Cosmological Context. And I think in astrophysics, like there's a whole bunch of questions that could come up. Like, why should we care about dwarf galaxies? What are small scales? Like in astrophysics, small can be pretty big. And also, why is the cosmological context important? And especially, why would it be important for dwarfs? And so I'll talk about the first one right away, and I'll try to answer the other two as I go along. So in German, we say roter Faden. It's like the common thread through my talk. So what's my common thread? I'm going to motivate dwarf galaxies. I'm going to talk about the LYRA model and what makes it different from other cosmological simulations. Give you the first results. I'm going to list some science cases, but I'm not going to go deep into that. But go more deeply into 2 examples of ongoing projects, and then an outlook for the future. So, as I said, why should we care about dwarf galaxies? Here are 4 dwarf galaxies in and around the local group, and they really look fairly uninspiring, maybe, to some that are used to looking at beautiful spiral arms. But they are what we think are the first galaxies to form in the universe, just based on hierarchical galaxy formation. The first ones have to form first, which also makes them pretty much the building blocks of all more massive galaxies, bar smooth accretion. They are tiny, and so they are really sensitive to a whole bunch of astrophysics that can hit them, which makes them record keepers for a lot of these things. And that's what we try to use. And when we take apart galaxies and try to look at what happened to them, we can find a lot of cool astrophysics. They're extremes. And I think in any type of science, extremes are always good because they delineate our knowledge and our categories. And so they're really extreme in many ways. They're the oldest, the most metal poor galaxies, the smallest, the least luminous, which makes them really hard to detect anywhere beyond the local group. And they have strange kinematics often. One big question and interest in dwarf galaxies is also in terms of their being the contributors for photons to the reionization of the universe. If we look at how many photons we need to reionize the universe, we really need to actually, if we assume it's all from galaxies, all from stars, then we have to really integrate all the way down to really small luminosities in the luminosity function to get the correct number. So I think dwarf galaxies are becoming a prime candidate for drivers of reionization. And then lastly, if you care about the Milky Way, they are the ones that when they fall into a larger galaxies become satellites. Here's kind of a map of the local group, and the Milky Way and Andromeda, and the blue line here is the zero velocity surface. So everything outside this circle is moving away from us with the Hubble flow. and everything within will stay with us. The red circles are 300 kpc around the Milky Way and also 300 kpc around Andromeda. So the gray dots are all things that we consider satellites. And the black dots are all things we consider field dwarfs. And there are definitely also some beyond this projection, but it gets limited pretty quickly. But many of these black dots were really only detected in the last 15 years. And so I think we're starting to, analyze them. And I think we need models dedicated to dwarf galaxies to try and understand them. So why did I develop the LYRA model? Aren't there enough galaxy formation models on the market? Can't we just simulate a few dwarfs? And that's been done, but I have a few reasons. So most previous cosmological simulations have set goals to either simulate a Milky Way or large scale structure even. And so if you have that as your goal, you have certain modeling choices that make you go away from the scales of dwarf galaxies. So just to give an order of magnitude estimate here, the mass of the Milky Way is around 10 to the 12 halo mass, and a dwarf galaxy is around 10 to the 9. So there's a factor of like 1,000, 3 orders of magnitude here. And in radius, it's kind of the same. So the radius of the Milky Way is around 300 kpc. A dwarf galaxy on average has a real radius of 30 kpc. So we have a factor of 10 per dimension here. So if you choose to study dwarf galaxies, you actually have a huge range to work with to make galaxy formation models better. So first thing to make better. Here's the density and here's the temperature. So in simulations, we call this the phase space. I know there's other phase spaces in other areas of science, so I do like to mention the axis. And in something like Eagle, but it's also very similar in Illustris and other simulations. So I'm not trying to like point any fingers here, just as an example, this is kind of a phase space distribution of the gas in these cosmological simulations. This up here is shock heated or feedback heated gas. This central part here around 10 to the 4 Kelvin is atomic cooling gas. And then if we had molecules and other low temperature lines, dust cooling, a whole bunch of other things, this would populate this circle down here. And if we then become even denser once we're cold, we would find ourselves somewhere down here where maybe stars could start forming. This space, as you see, is not populated. Instead, we have this weird little tail, and that's gas. All the dense gas is hidden away in this equation of state. So as I said, I have a bit 3 orders of magnitude to play with here, so I can get rid of all of this and repopulate my phase diagram with something that actually fills the gaps. And I don't have much shock heated or feedback heated gas, and that's just because it's a dwarf. So the other one was a much bigger system. But you can have gas up there. And then what happens, of course, if you do allow molecular and other low temperature cooling, then you can actually get a clumpy mixed interstellar medium, ISM, and you get something that might look like molecular clouds in the simulation. Okay, that's the ISM I've changed. Now I also changed the treatment of star particles. So previously, a star particle is often something like some gray blob that's maybe 10 to the 3 to 10 to the 5 solar masses. And hidden away in this gray blob is an entire single stellar population. All its attributes are integrated attributes of an IMF, initial mass function of stars. And that also means that any feedback return, for example, from supernovae, is just a time integrated death time of a certain fraction of the IMF, and you integrate over that, and that's the energy you put into your ISM as your supernova feedback. This has a whole bunch of problems. I'm not going to go into it in huge detail here, but there's a whole bunch of literature on why this is problematic. And so what I've changed is I've broken this particle up into its actual constituents. So I have individual stars with individual masses of their stellar mass, which is just important, not because it's cool, but because we then spatially and temporally start locating both star formation and stellar death, meaning supernovae or black hole formation or AGB returns. And so that means that the energy and the chemical yields that come out of stars are temporally and spatially actually resolved in the simulation as best as we can do. Another thing we can do is actually give each supernova a different amount of energy. So I know this is controversial and people will complain about supernova explosion models, but they're doing the best they can, and I definitely don't know better. So I'm taking the results from work by Supbolt et al. In 2016. And so the x-axis here is the stellar mass, so literally the mass of a single star. And then the x-axis on the top panel is the energy of the supernova of that progenitor mass at death. The dotted line is your fiducial 10 to the 51 ergs that most cosmological simulations put in for every single supernova. Instead, I'm putting in a very non-linear, non-monotonic distribution of energies. And interestingly, as you can see, what a major change this causes is that there's actually a whole range of very high stellar masses that we think don't actually explode as supernovae, but form direct collapse black holes. And so this is accounted for here. Bottom two panels are mass return. So this is at the moment still wind plus supernova ejecta mass returned to the interstellar medium at death, and metal mass. And so this is this cumulative metal mass, but I also do track 9 different elements. Okay, third thing I've changed in the code is the treatment of supernovae. And this, again, there's a whole bunch of literature on this, and probably a lot of you know these issues kind of all clumped together in the term overcooling. So if you have a typical supernova, there is an analytic solution called the set-off solution, where it is assumed to be a thermal bomb, effectively 10 to the 51 ergs in this case, put in as thermal energy. But as the shock evolves over time, you actually produce kinetic energy in the gas. So there's a transfer and an exchange into momentum or kinetic energy. And our analytic solution tells us that the max amount of kinetic energy you're supposed to receive is 27% of the input energy. A common cosmological simulation that is not well resolved will produce something in kinetic energy that looks more like the red line here. And so what we've realized is if you don't resolve either temporally the shock front or spatially the shock density, you don't get the required kinetic energy. And so to answer the second question on my first slide, when I mean small scales, I mean scales able to resolve the energy input of individual supernovae. So at the moment, I'm running all my simulations at a gas mass resolution. So this is a repo, gas cells, each have 4 solar masses. What does this look like in practice? This is direct little videos I made from cosmological simulations, and I'll go into a bit more detail about them in a sec. But just to give you a first glimpse, this is a redshift 8 super bubble right here that forms a beautiful bipolar outflow in this hourglass shape. At redshift 4, more star formation, different ISM, and we get a much more wild structure in our supernova explosions, partially due to the fact that stars are clustered, supernova explosions become clustered, and so you have multiple supernova explosions going off within the bubbles of previous supernovas. So you get this very complicated structure. By the way, this is not a time evolution. This is just rotating around a bubble to give you an idea of its morphology. So just to sum up, so you know, keep in mind what the LYRA includes. It does include the large scale structure. It is a cosmological simulation, started from redshift 128 all the way to redshift 0. which means it has a fairly realistic merger history. It does include individual stars where we resolve the IMF. This means we can put in individual supernovae where we try to resolve the cooling radii. It does have a multi-phase ISM, which means we get a clumpy structure that looks like giant molecular clouds. And also the beautiful thing about these two in combination is that the supernova explosions will actually interact with the clumpy interstellar medium. And that can produce clustered star formation. And it can also produce supernova outflows, so a realistic CGM around the dwarf. That's the modeling part. If you have any questions, ask them. Otherwise, I'll move on to the actual simulations. Yes. No, magnetic fields are not yet included. So REPO does have a magnetic field package. And we have run some tests with it on. Ones I'm going to show today, they're not yet included. So I can tell you that the preliminary tests don't change that much, but that the tests were in isolated non-cosmological simulations. So future results. Okay, so I've been working since the model is like kind of complete. As is clear, you know, models are never complete. You can always add stuff, but it's fairly sufficient, I would say, to model some galaxies. So I've started running a kind of a suite of LYRA dwarfs. My target mass is a few times 10 to the 9 halo mass. And during run, you know, they start, of course, with no stars at high redshift. They form about between 10 to the 6 and 10 to the 7 in stellar mass during their runtime. As I said, they run at 4 solar mass resolution with the hydrodynamic code of REPO. And already in this surface brightness image at redshift 0 of the one system, you can see two components. One is the clear kind of spheroidal, elliptical, diffuse, larger structure in the center. And then you can see a whole bunch of little luminous substructure. And this is already different from previous simulations. So that's one kind of emerging result as you go to better and better spatial resolution and mass resolution, is that you start seeing a whole bunch of even smaller substructure. And ongoing work, I don't know exactly what they are. Are they satellites of dwarf galaxies? Are they globular clusters? Are they just star clusters? Are they even real? Are they numerical artifacts? These are all questions that now that we've gone to these higher resolutions, a whole slew of additional questions start opening up to simulators to try and understand. So that's just one exciting result, I think. It's not clear what it is, and it's work in progress. So as I said, I'll go into a few first results. And these are all just redshift 0 comparisons to local group dwarfs, with the unfair comparison that all my simulations are isolated, like field dwarfs that don't interact with something like the Milky Way. And a lot of these gray observation points are actually, I mean, some of them are field dwarfs outside the local group, but some are not. So it's not the best comparison possibly, but the only comparison at this point, because we don't have that many observations of these systems. So top plot is the stellar mass and the halo mass. And there's there's 5 colorful diamonds. The light blue one, as I put in the legend, is still running. So it's most likely still going to move across to the right. But those are the 5 simulations that I've run so far. The purple squares are Fire 2 dwarfs from Coral Wheeler. The blue circles are also very high res galaxies that are from the EDGE project. So Oscar Agart's group and others. Anyway, and the 3 lines are abundance matching extrapolations. So as you can see, we have like 3 orders of magnitude to play with here. So they're not particularly constraining. What we can say is we're kind of on the high mass end, but we're very similar to the edge dwarfs. The magnitude metallicity relation is been a trial relation that a lot of simulations have had trouble matching. And there's work that shows that if you change the strength of feedback, you will sort of wander across the relation diagonally, meaning that feedback, like getting the relation right, kind of tells you a bit about the fact that you've gotten your feedback right-ish. And so the fact that we go to the effort of going to high res, looking that we actually resolve the supernovae, seems to pay off because we're sitting pretty much within the scatter here. Another interesting plane to look at is the stellar size magnitude plane. So this is the half mass radius on the x-axis and the V-band magnitude on the y-axis. These dots over here are Milky Way globular clusters, just to give you like a context. So they're really small, but fairly bright. These down here are the ultra-faint dwarfs that have been detected recently. So they're, as the name says, fainter, but actually bigger, and they clearly have dark matter. That's why they're considered galaxies and globular clusters are not. And then up here, these are the classical dwarfs. And as you can see, we definitely sit within that regime. I mentioned kinematics a little bit, and I'm not going to talk too much about it, just for the sake of comparison. We sit within the rotation, like that the leftmost panel is the circular velocity in stars. The middle panel is the stellar velocity dispersion. And this panel is their ratio, which gives you understanding of whether or not you're being supported either by rotation or by dispersion. And as you can see, we sit in the dispersion dominated regime. And so what we can also conclude, other than the fact that they're classical dwarfs in size, is that they're actually in line with like dwarf spheroidals that we see in observations. One last thing on comparison, except this isn't really a comparison because I'm not showing the observations, but there are reconstructed star formation histories and of local group dwarfs. And so I am working to do an accurate comparison with them right now. These are the 5 different star formation histories as a function of time. The last one's still running. And then as you can see, the top one and the middle one are what we call like reionization relics, classical star formation until onset of reionization at around redshift 8 or 7.5, and then they go dark for the rest of their life. And so this is completely ancient population is consistent with various observations. So Draco and Andromeda 7 are both consistent with only stars pre-reionization. And then we have these other interesting ones. This one has more star formation before reionization, but it has ongoing star formation almost like very bursty, but almost until redshift 0. This one, on the other hand, stops forming stars and then suddenly rejuvenates and decides it actually wants to be an active dwarf again. And I think that this is really interesting. There's a few reasons why this can happen. So as the system merges over these 8 billion years, the halo mass grows, the potential grows, so it's just able to capture more gas. On the other hand, the stars that did form, some of them only die very late, so they're still emitting some metallicity into the interior gas that is at that point hot, but then becomes metal enriched a little bit. And also towards redshift 1 and below, the UV background starts declining again. So all these in combination can actually give you favorable conditions for cooling. And the other thing is that once you get a tiny bit of cooling, as long as you can get past the like hydrogen self-shielding threshold, then you can form stars really fast. So you don't need to like you don't need to get to the density of star formation right away. You just need to get to the self-shielding density with these things. and from then on you can you can go again. This one's still running. It looks like it's going to continue forming stars forever, and that's my biggest system. That's why it's also still running, but it's to see.
It's more or less because the potential whale is deeper, so yes, wind is not efficiently blowing up material, right? It's like continuous star formation in the most massive one.
Yes, so definitely there is a mass trend. So they are ordered in mass in finals, halo mass at redshift 0. So it's not entirely continuous. This one is less massive at higher redshift, thus stops. And even though it catches up to this one at redshift 0, it doesn't end up forming stars again. So it's not only the final mass, but the growth history. So because if you can grow like this or you can grow like this, and that'll affect your high redshift evolution. Okay, that was a whole bunch of mostly redshift 0 stuff. So what simulations can do is give you intuition on what happened to high redshift. And the way I'm going to do this today is just through videos because they're fun. So this is the gas density across time. You can see redshift and time up there. And what you will see is the effect of reionization. So this is one of the reionization relic systems. And what you see is the gas, of course, follows the dark matter. So it's collapsed into a little filament and does form stars in the densest peaks you see. And as reionization sets in, everything gets photo evaporated. So this is not just my resolution going really bad in my simulation. This is literally the effect of reionization, heating up the gas, photo evaporating it out of the potential wells and smearing everything out. And that's why star formation stops. Same exact image location. So the little filament's still here. We're looking at gas temperature now. So there is star formation all along this little filament, and as the stars die, they explode, and we see a whole bunch of heated gas in bubbles caused by exploding supernovae. And as you can see, as they kind of flicker, it's actually multiple supernovas going off in close proximity. And as reionization sets in, as you'll see, the background heats as well, and the entire system smears out again. So that's the effect of reionization. So this is also very clearly showing that while it looked hot relative to the background before reionization, it's still such a small system that it's not really hot in like a global sense, because reionization only heats to like 10 to the 4 Kelvin. So anything that is that temperature just becomes equal. Same image again. Now gas metallicity. So of course the supernova inject both thermal energy and chemistry into their vicinity. And the explosion, of course, helps the chemistry be mixed and be distributed along this filament. So what's really interesting to think about with this image is that all of the individual star formation sites are at this point in time not one system. They're all individual little systems. And so each one is contributing its little bubble of enriched material around it. But what ends up happening as then finally also the main system starts evolving in the center is that the entire region that is enriched is actually much bigger than what you would maybe expect if you just had one system enriching and forming stars in one location. So you can actually get a very large enrichment footprint from this filament and later merging. Last video, and then I'm done with the videos. This one is stellar light, so V-band surface brightness. And I fast forwarded a bit in time and I've zoomed in. a whole bunch to a very small system, to the very center here, because the stars are small. So as I said, there's a whole bunch of little substructures. So these are all these mini halos that manage to form like tens to thousands of stars and just sat around, got quenched by reionization, and then end up merging. A lot of them at least end up merging with the main system. And then there are also more major mergers that change the way that the stars are distributed in the halo. So as this progresses, you'll see more and more why the final morphology is a dwarf spheroidal galaxy, because all of this material gets redistributed over time into a big circular system with a whole bunch of substructure. So I'll just let this play out and then I'll go to my next part. So yeah, you can see kind of like it's a bit elliptical, extended shells and constant merging of tiny little systems. Right. One thing I wanted to say here for my third question at the beginning, why is the cosmological context important? And so all of this structure and the fact that it becomes a dwarf spheroidal is because of its accretion history, its merger history. And so if you don't have the cosmological context, you don't get the same morphology. So that completes my 3 points in the title. Okay, I'm not going to go into this very much. These are a whole bunch of ideas I have of science cases I can do with finished simulations. They kind of categorize into 4 main groups. Local group comparisons, some I've already shown you, and others. More interest on high redshift assembly and evolution, reionization as a huge impact on dwarves, and lastly, the circumgalactic and intergalactic medium. So I'm going to talk in detail about 2 ongoing projects. The first one is like the contribution to the intergalactic medium pollution. And I'll explain in a sec. And the second one I'm going to talk to you about is POP3 stars. So first ongoing project is the intergalactic medium. And so why is this important and why is it of concern? So if you use quasar absorption lines to study the chemistry within the intergalactic medium, you can get absorption lines. And so, for example, you see magnesium-2 in a whole, in pretty much all over the universe. And if you categorize your absorptions into either weak absorptions, little systems, or large absorption systems, and then plot how many of those systems you see as a function of redshift, you get a totally different result. So for the weak absorption systems, it's pretty much a constant. So you see the same amount of magnesium-2 across all redshifts. For the strong absorbers, you don't. You see a very strong drop towards high redshift, and you only get to the equivalent value at like redshift 4 or 3. And so the question is, why does this happen? And my question is, are dwarf galaxies responsible for this? And so what I did is to create mock column density my systems. And this is as a function of redshift. So redshift 9, there's almost nothing. Redshift 8, huge amount of star formation, and bubbles have already appeared in the meantime. And so you get a huge footprint. By the way, the black contour is the threshold for weak absorption signals. Redshift 7 starts decreasing, and by redshift 4, you're back to something that's as small as you might expect if it was just a tiny little system. And so this is work in progress, as I said, but this again is the weak absorption observations. And if you look at this fat red line, then you see that there's a discrepancy between the observations and this line. And the line is if you take something like a lustrous TNG and you integrate the mass function or the luminosity function down to a fixed mass cut, that helps you match the values up here. And then you look back, does that help you match the values at high redshift? And it doesn't. There's a huge discrepancy between what we should expect if we have a fixed contribution from a fixed luminosity, like down to a fixed luminosity. And so if you look at the absorption of the weak absorber threshold, so these are 4 of the systems that I've been showing you. And as a function of redshift, the footprint of magnesium-2 above the detectable threshold. And you can see that it pretty much is big and drops exactly down at like redshift 3 or 4. And so I still have to make the like apples to apples comparison here. This is absorber size, and this is just weak absorber signals. And so, but I'm hoping that it will come out to fill this gap here. So that's my first conclusion, is that dwarf galaxies may be the dominant polluter at high redshift for weak absorption. I don't have too much more time, but I'll show you my last, and that's it, last ongoing project, halo masses of POP3 stars. So what does this mean? Why do we care? POP3 stars are what we think, no one's ever observed them. They're postulated as the first stars that ever form in the universe from metal-free gas. And then as they die, they eject the first metals into the universe. But we don't know if they exist and where they form. And so there's different projects to try and model this. And these data points here and this black line are 2 different models that try to narrow down what halos, so what mass halos POP3 stars would feasibly form in at a given time. And as you can see, they don't agree, and they also go across a huge span in mass. So the kind of take home from this plot is we don't really know, but it can be anywhere from 5 times 10 to the 5 to like 10 to the 7 halo masses, solar masses. Yeah. And so I added a little tiny like model to my simulation where I modeled 3 different ways to introduce metals into the simulation. The first one is the homogeneous one. So that just is the way that pretty much all cosmological simulations do it to date. It just puts in gas at very high redshift with a tiny little bit of metallicity. So mostly like 10 to the -4 solar in relative to solar. So technically really small, but still more than we know should be there. And it's also just homogeneously throughout all the gas in the box. So I decided to change this a little bit and say, okay, what if there are POP3 stars and they are the ones who create those first metals? What if they all form in 10 to the 6 halos? So then you'd start your box with 0 metals, and only if a halo crosses that mass threshold, you put all the gas within the real radius, you enrich to your 10 to the -4. Or you can test a different one just as a kind of an outlier model, so 10 to the 7 instead. And what does this do? How does this change? So the number of lumina substructure is entirely dependent on how you treat the first metals in a dwarf. So this is, again, a function of redshift. Here's your reionization. And this is just counting luminous substructures, so anything that has at least 1 star within the virial radius of the main halo over time. And so as you can see, there's a break at the reionization. So that's because before reionization, everything's forming stars and there's a huge amount of outflow happening. But once reionization happens, if the star formation is either quenched or decreases dramatically, the outflows stop. And so what actually happens is that your velocity field ends up turning back around and you start accreting. And so that starts accreting all these mini halos that were not part of your main halo into the main halo. And that's why suddenly you get a huge up shot of all of these numbers, but the final redshift 0 value is totally different between the 3 models. And so this is something that like not that many people have thought about or looked into. We kind of just do this and keep going. And so I think this is important to look into more deeply. And then the other thing is that you can actually switch your argument around and say, well, if we actually would be able to observe dwarf substructure and count it, we might be able to constrain the value of your POP3 halo mass. So the predictions for example, Vera Rubin or the LSST survey is, if you look at the blue line within the Milky Way virial radius, they will be able to find objects all the way down to V-band magnitudes of -2. So they should, if there is dwarf substructure, they should be able to start finding it. And that's it. So that's me. Just to summarize, LYRA is a galaxy formation model that tries to bring together small scales of baryonic mess and the cosmological context. It does, by going to these smaller scales, it opens up a whole slew of new questions, but also possibilities, of course, of how to do the analysis and what we can try to understand about galaxy formation. Model developments are planned. I have tested radiation and magnetic fields, and a whole slew of things are planned. And lastly, dwarves are not the end. They're really interesting in and of themselves, but I'm also pushing towards more massive systems as I progress. Thank you.
A very nice talk. And is there any question?
Thanks for the great talk. If you just go back to the last slide where you were talking about, dwarf galaxy substructure and how future observations of that might be able to inform basically whether it's the heavy halo or the lighter halos that are seated with the POP3 stars, the metallicity. Do your model also, are you able to predict basically the distribution of remnants from POP3 stars in these two scenarios? Just because next decade with third generation gravitational wave detectors, we will hopefully be able to measure the mergers of remnants of POP3 stars. So I'm just wondering if that's another observational angle where you can distinguish, these scenarios.
Whether I can predict a chemical signature.
Yeah, I guess I'm asking in LYRA if can you model the distribution of remnants of POP3 objects coming from these two?
I don't POP3 stars themselves.
Gotcha. You put in just the metallicity.
I only model their halos.
Right. I see.
In this granted very simple model.
So my next question is actually show in the early slide that actually stellar mass halo mass relationship is quite different from what fire has predicted. It's by order of like 3 or 4 order of magnitude. So do you think it's like your model has something to improve, or you think that fire is wrong?
I think we're going to meet in the middle. I think fire is going to go up and I'm going to go down and we're going to meet somewhere here. That's my prediction. So
what would be the difference? Like what is the feedback prescription do you think made those large discrepancy?
So there's a whole bunch of stuff. The way the supernova are handled is different, but that's probably not the primary cause. But I think the fire simulations include a prescription for H2 regions or photoionization feedback. And I think that affects, like, it's very important how you model the first few mega years before the first supernova goes off in a star cluster. And that, like, if you have early radiation and it's strong, its effect is strong, and then you can suppress a whole bunch of star formation in those 3 mega years before your first supernova goes off. And that's something that I'm missing in my model. On the other hand, as I said, I think that the fire stuff is going to go up. And I think that's because also just looking not only at their dwarfs, but all of their galaxies, they're generally fairly bursty and the feedback is extremely strong. And so I think that's probably a little bit too strong. And I think there's, as far as I understand from other people in the FIRE collaboration, there are changes to that now.
Oh yeah, yeah, sure.
So
Yeah.
I always worry to point fingers. I don't know, like I'm not part of that group, but yeah, as I said, I think we're gonna find our way into the middle here, probably.
So just to follow up on that question, like look at this plot. Is it fair to say that the FIRE sims would have difficulty matching the abundance that's seen, you know, for classical dwarfs, and this is
So they are fire are all not on the relation.
so therefore they do have difficulty matching, or
I haven't put them here, so I don't exactly know where they sit, but I think some of them are significantly low. Yeah. And yeah, as I described, I think this is a way to kind of test your feedback strength. And so I think that makes sense, that they're very low there and they're low here. And so reducing their strength of feedback a little bit will bring them up here and there. And as I said, my model doesn't include early feedback forms. So that's why I think mine will come down. Any questions from Zoom?
Juna said thank you.
Okay, well, if there's no other questions, thanks.